אבל אז הם נשמעו אותי. הם לא יכולים. אוקיי, אני צריך לראות שאין פידבק. כי כאילו אם אני אהיה מוכוון צריך להשתיק פה וגם להשתיק את הכל.
אז הנה, זה המסך שלך.
הוא לא יודע להתחבר לזה ולשתף את זה?
תתפתח
מה?
מהבית אנחנו רואים אתכם, המסך קצת חתוך מימין.
שומעים אותך, אבל חבל הזמן.
הקצה ימני של המסך חתוך מהבית. אבל שומעים אתכם טוב.
טוב, אני חושב שזה היה לקצה.
גם אני יכולים מאחורה שלי?
טוב, אפשר לשאול לך פלייסט.
הם רואים רק...
אנחנו רוצים לראות את הלינק. אני חושב לראות את הלינק.
שכל מרצה אחרי זה יכול לשמוע מורים על זה. אני עכשיו אומר לסטודנטים כל הזמן שאין לי בעיה שנדברו בהרצאה.
לא אסכולה.
זה לא שיש למרצה נעים בגב, שיש לו מיקרופון וקהל.
זהו, אז עכשיו אתה לא יכול לדבר.
זה נורא, זה לא יש פה דומה. סתם,
שלחו פה איזה גל קול שמבטל אותם.
קראתי עכשיו כדבר שאסור הרצאה
לא, אבל זה נורא פשוט.
יש לך את הלינק בוואטסאפ?
למישהו
יש את
הלינק של
הקישור שאני יכול
רואים את זה, יש שם לראות את זה בזום.
לא, אני פשוט לג'ימל, יוני, לג'ימל, אני מתחבר מהמחשב.
כל הנסירי. שבוע שעבר סרוח משל...
למי לשלוח?
אליי.
רגע. אבל אני לא חושב שיש לי את האימייל שלך.
אנחנו נצלח את זה. M נוקד,
הנה, הצלחתי שאני 892. הנה, כבר מתחילים.
מה, שאני אכנס לזום כאילו?
כן, זה זום,
זה פיצ'ר, זה פיצ'ר.
האמת אפשר גם דרך עם המצלמה, אבל בוא נעשה את זה.
גם אהבתי את זה
כמה סתם, אני לא נמצא
עם מיטים גיידים?
בטח.
איזה שם איקסים.
זה לא אספס.
פספס. באמת יש שם איקס שווה מורכז, אבל למה?
יש על העין לפעמים.
אוקיי.
רמקול. אוקיי, ככה שים תגיות. כמעט.
תבטל את ה...
טוב, אוקיי? יאללה.
עכשיו שומעים לו?
יאללה.
שומעים?
אתם שומעים?
אנחנו שומעים.
חוכמה גדולה.
בבית שומעים?
מה שהיה להוכיח.
נעשה שיר סרט.
כי עכשיו אין ספיקר, אבל אתה לא יכול לשמוע מהבית.
בבית שומעים.
אתה צריך לאפשר.
אבל המסך קצת חתוך.
כן, הבנו. המסך הוא עד הקצה, אז זה בסדר. מעולה. עוד לא?
אבל לא רואים שום דבר.
עוד רגע.
אוקיי, בסדר, אתם עושים שיירינג?
כן. אז אנחנו עוברים לאנגלית. So it is my pleasure to introduce a speaker today. We have Malachit Noker from the chemistry department in Bar-Ilan. He did his undergraduate in the physics department here and continued to a PhD in chemistry under the supervision of Doron Orbach, working on the various carbon materials for clean tech and other stuff, and graduated in 2013, continued to a postdoc where it was a Fulbright Ilan Ramon Fellow in the Energy Frontier Research Center in the University of Maryland, and returned to Bar-Ilan in 2016. He's an expert in energy storage, surface chemistry, atomic layer deposition techniques, and many other stuff. He was a Krill Prize laureate in 2019, and today he's part of the National Institute for Sustainable Energy, which is acronym NICE, and is located here in Bar-Ilan, and working on developing the next sustainable energy for Israel for the future. And today he'll tell us about his work. So, Malachit, thank you. The stage is yours.
Thank you. Just making sure that people at home are seeing the full screen. Because sharing the screen, do you see a full presentation mode?
Okay.
Yeah. Okay, good. Thank you for the kind introduction and for inviting me here. It's a pleasure. I'm just a neighbor, and present here is very nice for me. So I'm going to talk today about surface engineering of electrode materials. I know that some of the language we will need to find a common language, and I'll do so by introducing both the techniques of surface engineering we are using here in my lab, and also I will introduce you to battery. Because we are working with batteries. I hope we will then establish a common language between that. So the sticker back.
Done?
From home, we also see the preview pane, like the outline on the left.
Is it better now?
No.
Instead of doing extend screen, it would be better, I think.
So stop sharing and then share again, because otherwise I think it will not work.
No, but I think it's in a dual screen. It's in a dual screen mode, and then
yes, I will duplicate. That's it. What's duplicate?
So how can it be?
Yes.
Oh, but PowerPoint changes it to
The dual screen.
Screen top. Here it will show. I think now it will. Is it working now?
Yes, good now. Yes.
Good. Okay, so I will speak from here because the pointer. So I will talk today about our work on suppression degradation of electrode material. As I said, I will give short introduction to our techniques for surface modification, and I will also introduce you to battery. Well, my lab is located here. You are familiar with the nano building. We are neighbors to the group of Yoni Tucker here on the 7th floor. This is my team, and I'm trying to begin with thanking the funding agencies, because otherwise sometimes there is not enough time at the end, and this is really what makes helps us work. And the people that are really working in the lab and not just showing in seminars are the people here in the photo. My lab, the focus of my lab is designing artificial and functional interfaces. We are doing so in various applications. I will focus today, or the majority of our work is really related to energy storage material, what you see here, stabilizing the interface of active materials in energy storage devices. But we also have works on chiral thin films and also biofilm protection by thin film deposition. And we are designing the interface of materials to make it functional, even if it's completely blunt. So we take a regular material which has no chirality in it, and we modify the surface in order to make it chiral or non-selective. I will focus today on the energy storage material. So the content of my talk. So the content of my talk will be an introduction to atomic and molecular layer deposition. I will show to you, and I will briefly introduce you to the methodology and how it really works. And then I will also try to briefly introduce you to rocking chair batteries, how lithium-ion battery really works, and what are the mechanisms that dictate the operation of this battery. Why is surface film important in stabilizing active material in this battery? And then I will show you some results from our works. So brief introduction to atomic layer deposition. Naturally, we need to have some chemical touch here, but not too deep, don't worry. Okay, so if I take these two compounds, water, it's quite easy, and trimethyl aluminum, it's aluminum that is connected to methyl group. Now this is nearly methane gas, CH4 is methane. Okay, when we react the trimethyl aluminum with water, we will have alumina, aluminum oxide, and methane will leave. Okay, so far so good. Now if we take it in a beaker, or we react it in reactor, we will have just precipitation of alumina as a powder, and methane will leave. So chemical vapor deposition took it a step further. Chemical vapor deposition, there is a reactor. Inside the reactor is some kind of substrate, and we introduce these two as in the vapors as gas phase together into the reactor, and then we have coating on active material or any substrate of interest. This is chemical vapor deposition. Vapors of water, vapors of trimethyl aluminum are carried together with a carrier gas into a reactor, and there is a reaction to form a film. Atomic layer deposition is taking it even a step further. We have these two precursors. Here it will be a blue and red, or if someone can remember, the trimethyl aluminum and the water. Here we have fast belts, and the fast belts are opening between microseconds to milliseconds, depends on what we want. But there is always single precursor that is introduced into the reactor. They are not introduced together. There is alternating sequence of introduction of the blue precursor and the red. So this valve is open, only the vapors of the blue is going in, and then it is closed. We are evacuating the reactor, and then we open this valve to introduce the blue. And we are alternating the sequence, and a single cycle of ALD means exposure of the blue, evacuating the reactor, exposure of the red, evacuating the reactor. This is a single step of atomic layer deposition. Now, the origin of the name, why we call it atomic layer deposition, is here. So I will try to restart it because it appears only here. So anyway, I'll stop it here. You see, the surface is terminated with hydroxides, oxygen and hydrogen. This one used to be trimethyl aluminum. I will take it in a second back and you can see. Now, when the trimethyl aluminum is introduced into the reactor, the methyl is abstracting the hydrogen, and then methane gas is leaving. And now there is a formation of new bond between the oxygen and the aluminum.
So this surface of oxide hydrate is that naturally occurring? Or?
Yes, it's either naturally occurring or we can introduce it by pretreatment. Okay, so if I want to take any surface of interest, I can introduce hydroxides on the surface using special acid treatment. But this is possible. We can also do it inside the reactor. The cartoon is very nice, but it is very naive, but it's helpful for understanding. Okay, so the surface is terminated with hydroxide. Now trimethyl aluminum is introduced, reacting with the hydrogen. Methane is leaving, aluminum is bonded to the oxygen. And now another trimethyl aluminum, there will be a full surface coverage until there is no room. So this one cannot react, and this one can't react. Next stage, we are introducing the water. The water are introduced, reacting with the remaining methyl tails. And now we are depositing oxygen, aluminum, oxygen, atom by atom. And this is why it is called atomic layer deposition. We can put layers on very challenging topographies, high aspect ratios of various thin films of oxides, phosphates, nitrites. By controlling the entity or the composition of the alternating precursors and then alternating the sequence accordingly, we can control the functionality, the composition, and the properties of the deposited thin film. So if we want to have, instead of 2 compounds or 2 component thin films, we want to have 3 or 4 component thin films. All we need to do is just to add more precursors. This is what used to be done. We can have green and purple, and sorry, my color vision, yellow and purple, and we can start with lithium oxide, and then we can introduce a precursor for phosphorus, and then we can have a lithium phosphate, and then we can introduce also a nitrogen precursor, and we have a lipon. And this is very important because this one specifically is lithium ion conductive, so it's good for solid state batteries and also for surface protection. But it used to be that we introduce another precursor, and then we enrich the chemistry, we enrich the composition, and then we have a desired functionality. We are doing it today quite differently, as I will show you later on. The sequence, for example, the sequence for lipon deposition is composed of 4 precursors, and in between we need to evacuate. And sometimes we need also to introduce another oxidizing agent, but the process is very complex and it is very challenging to upscale these processes. We are trying to shorten these processes into two reactions. I will show you later on.
How much time is cycle takes?
So this is a very good question. If I need to have a thin film on a flat substrate, it can be 1 second. Can be 30 seconds, 20 seconds, depend on the aspect ratio. For powder coating, what I show you here is we coated an active material of iron oxyphosphate fluoride. What we did here, it takes longer than 1.5 minutes per cycle. So if we want to have 100 cycles, it's going to be 150 minutes. It's not scalable. Okay, so it's challenging for the industry to do so, and we are also working on. We are trying to aim both for fundamental understanding of the importance of the thin film, but to be practical. So what you can see here on the left is an example of lipon coating on active material. This is a powder of iron oxyfluoride, and we are capable of coating it with lithium-rich compounds with a very thin or controllable uniform film on the surface. This is the approach we are currently taking in my lab, meaning instead of alternating sequence of various precursors, we are designing the precursor a priori. In this case, we take sodium terpetoxide with this precursor. Forget the name, it's a long name, we can call it DEPA, okay? And then in a single precursor, we can introduce phosphorus, oxygen, and nitrogen, we do not need to introduce 4 different precursors in alternating sequences, but we can use 2. Here we demonstrated that with a napalm coating. Instead of lithium ion conductive, it's a sodium ion conductive film, and we can coat powder with only 2 precursors. This is the ALD setup. If anyone is interested in coming and trying to coat material of his interest, this is how it looks like. We have ELSA is connected to a glove box, because here we can coat metals which are highly reactive, like lithium or sodium. We can also develop films that are sulfide-based, that are also reactive, so the film itself might be reactive, and we don't want it to be exposed to moisture or to oxygen, so it is closed in argon-filled glove box. This is the ELSA condition. Anna, I did not choose the names, obviously, but Anna has the plasma unit in it, so we can coat nitrides, dinitrides, is already developed in my lab. We have also some attempts to develop niobium-based chemistries, and we have plasma unit over there, and in both systems we can coat powders. To the machine itself, we have 6 different precursors that are connected, and we can also have 2 more oxidizing agents or reducing agents. How we coat powders. This is how the powder unit looks like when it is open, and you can see the tumbler here is rotating. We can control the rate of rotation. This is obviously open. When the reactor is operating, it is closed. You can see the nozzle here is going into the tumbler, and therefore we can coat powders. So examples of powder coatings, we have alumina over silicon. We have thin alumina over active material for lithium ion. I will discuss more later in this talk. This is another thin film of more complicated chemistry of lithium vanadium oxyphosphate on a surface of carbon nanotubes. You can see that the carbon nanotube is conformally coated except here, and there used to be another tube over there. This is a challenge for us to overcome this kind of entanglement of the carbon nanotubes. This is another work of lithium silicon oxide. So it's a lithiated silica, which is coated through the use of only 2 precursors, and so on. We have molecular layer deposition of various kinds. And this is, for example, we take, instead of water, we can introduce hydroquinone, and then we have this ring within the film. So it's a molecular layer deposition instead of atomic. We put aluminum and then the molecule, and then aluminum and the molecule. We are capable of controlling the chemistry and also the mechanical properties of this film. This is a metal organic framework developed together with Professor Idan Rod from Ben Gurion University. And this is in a collaboration with the Banim group here from the biology. This is a nicotinic acid to form a thin film, which is biofilm protection. Okay, so we took it a step further. The atomic layer deposition. We are using, I will show you 2 processes. One is using a single precursor for only reduction. Instead of using 2 precursors, I can take advantage of the fact that the solid or the material inside the reactor is already rich with oxygens. So I'm using the oxygen from the material itself. And by introducing a reducing agent, I'm just coating it conformally. And the second one is multi-atoms deposition from a single precursor. Okay, so instead of having 2 alternating precursors, I can have only 1. In this case, it will be, I will give you an example of trimethyl aluminum. We take the substrate, which is oxygen rich. In fact, in some of the material, this is a challenge of the material. One of its degradation mechanism is related to the oxygen evolution from the surface. And we are using this oxygen in order to coat the material conformally. Here you have, it's a schematic done by one of my students. Before we took it to calculation, you will see that we have also support for that. So it's trimethyl aluminum is introduced into an oxide containing, the material is oxide-based. This is the composition. It's an oxide of nickel, manganese, and cobalt, and the trimethyl aluminum is introduced in the vapor phase and reacting with the material itself. We do not need water and we don't need ozone. We collaborated on that with Dr. Kevin Lehan from Sandia National Laboratories, and he really showed that the decomposition of the trimethyl aluminum is spontaneous on the surface of lithium cobalt oxide, which is the currently most common oxide for batteries. The lithium cobalt oxide, when trimethyl aluminum is introduced, it will spontaneously decompose on the surface of the lithium cobalt oxide. This is the most reactive facet, and this one is also, it's in the middle in terms of reactivity, but this is quite common. And you can see that the trimethyl aluminum is bonded and decomposed spontaneously. Another interesting observation was that when we take it to a more complex oxide, the trimethyl aluminum is then bounded to the transition metal within the oxide and reducing it. That was the theoretical observation, and we were there in the next work, we were able to show it experimentally. Following with XPS the state of the manganese, we were able to show that the manganese is indeed reduced. When we introduce the trimethyl aluminum, the precursor, the manganese is reduced. So the mechanism of reaction is quite solved, not only by us, but follow-up work of the group.
Can you define reduction? I mean, what's the meaning of reduction?
Yeah, so you start, if you, I will define it now, okay? This is a very good question. So if you start with manganese 4+, you will have instead a manganese 3+. Also, you are reducing the transition metal within the active material itself. So it's an oxide of manganese. This is not from us. This is a follow-up work that a group from Argonne National Laboratory was reporting the same finding. And you can see that here it was easy for me to demonstrate the reduction because they really pinned the manganese in their work, showing that the cascade of reaction of trimethyl aluminum on the surface will end up in reduction of the manganese itself. So the oxide is not only alumina like we used to see with trimethyl aluminum and water. There will also be at the end, manganese is also involved in the bonds to the oxygen by changing its oxidation number. This is how it looks in high resolution TEM. This is the active material before coating, and this is how it looks after coating. We can have a conformal 3 nanometers in thick, in thin, 3 nanometer thin coating over active material. And this is what we can do with only a single precursor. The good thing or the interesting thing about this process is it is really a self-limiting reaction. At some point, the trimethyl aluminum is no longer capable of diffusing and reacting with the transition metal. So the reaction just killed itself. So it's a self-terminating reaction. We have a very thin film, and you can see that depends on the precursor and on the substrate. The termination of the reaction will take place at different stages.
So what do you mean by conformal?
When I look, so this is a very good question. When I speak on conformality, it's always a question of statistics, or it might become a question of statistics. I can't. In a lifetime, I cannot take all the particles in the reactor and look in TEM and make sure that everyone are coated. This is it will kill my budget, but it will also kill the time of the high resolution TEM. So it's not possible. What I mean by conformal is that any particles we look at is coated. So we took many samples, maybe 10 from each batch and different locations, and they are all coated. When you compare it to the bare one, it is uncoated. This is what we can do. And we can also show it with XPS. You can see that there is a suppression of the transition metal peak, which means that it is coated, and we can also support it with solid state NMR. But we can't say that all of them are, every single secondary particle is coated. We just don't have a good way of proving that. Okay, now, the second approach we are taking is instead of using, for example, 3 precursors in order to coat our active material, we can take a single precursor which combine the yellow and the blue one to become a green. So in a single precursor, we have 2 colors, or we have 2 elements of interest. This is an example. This is in a collaboration with Professor Yitzhak Apeloid from the Technion, and also helping us in understanding the interfaces, the group of Dr. Michal Leskes from the Weizmann Institute. Today, we are capable of using this compound. You can see that it contains silicon, zinc, and lithium in a single compound, and by only alternating 2 precursors, this one with ozone, we have coating of lithium zinc silicon oxide in a single thin film. Based on 2 precursors, instead of, in this case, we needed to have at least 6 steps. Why is that important? Well, this is another, this is the first work on that with Professor Apeloi group, where he developed a lithium compound that contained silicon and lithium, and we were capable of depositing thin film on active material and also allocate the mechanism. But I want to go, how is it relevant for batteries and why is it important? But for that, I need to introduce you to batteries, which is a completely different aspect, maybe a short introduction. And then we come back to see how the surface film is improving the battery performance. Okay, so whoever missed the introduction for atomic layer deposition, which took me quite long, and I will now introduce you to batteries. Okay, so we're all familiar with the change, right? We have electric vehicles and we have units that are coming today, which are large energy storage units. They are all filled with batteries. How it is first packed in a full battery pack, it will look like that. These are the values that we will talk about in a full battery pack. It's just the normal values between 30 to 50 kilowatt hours. Every pack like that is composed of battery management system and a module. And even the module is then composed of single cells. Okay, so now I'm taking you into a journey of zoom in into these systems. This is the battery pack, module, single cell. Now every single cell, you can look on cells in various form factors for lithium-ion batteries. There are prismatic cells, cylindrical cells, and also pouch cells. They will all, inside them, will be composed of layers. And these layers are actually active material, which is pasted on current collector. More zooming in. This is how it looks from the inside. There is a unit cell. So this is the aluminum current collector. On the aluminum current collector, we will have the cathode. On the negative, we have copper current collector, and on the copper current collector, we will have the anode. These are about the dimensions of the layers. So every coating is maybe 80 microns in thick. And here we will have a separator, which is electronically insulating, but ionically conductive, because it's filled with electrolyte solution. So it's filled with organic solvent with lithium salt. I will go even more zoom in soon. But this is the structure of inside the battery. Questions?
What's in between the collector and everything?
This is the aluminum current collector. The reason why it is aluminum is very interesting, but not for now. This is copper current collector. It's a challenge because it's very expensive and heavy. This is a separator. And this is the anode pasted on 2 sides of the copper, and this is the cathode pasted on 2 sides of the aluminum. When we really zoom further in, we will see that the pasted material are actually, it's a paste, so there is a binder, and there is the particles of the active material. This is the cathode side, and this is the anode side, and this is about the dimensions of the particle itself. So every particle is about 5 microns in diameter, but it's actually many nanoparticles that are collocated together. But this is the zoom in journey into a battery. And what we are doing here is really focusing on the active material. This is what I'm showing you today. So there are many works on the separator. There are works on the current collectors. We are focusing on the active material. This is what I'm showing today. But for that, we need to understand why material is active and what are the principles for activity in rocking chair battery, and then we understand why we call it rocking chair battery. So 2019, these are the 3 important laureates for the Nobel Prize in chemistry. We will try to understand what they found. So these are the cathode people, and here's the anode. It's more than that, but so first demonstrated disulfide layered materials as cathode, and then they found of the lithium cobalt oxide. They did way more. And this is the anode, which is carbon-based. And we will try to understand what is the mechanism. So think about 2 different phases, and here I try to keep it simple. blue phase and a green phase. And the blue phase really is a donor. He wants to give electrons to a green phase. If I will put them together, there will be a spontaneous injections of electrons from the blue phase to the green phase. And in order to compensate overcharge, because we are injecting electrons, there will also be a movement of cations. So this is a compensation overcharge. So two processes occur. One is the electrons, and the second one is the ion movement. This is not good because we cannot control the movement of electrons, and we cannot send it through a consumer. So in order to overcome this challenge, we separated the blue phase from the green phase. The blue phase really wants to reduce the green phase, but there is here electrolyte which is electronically insulated. So there will be no movement of electrons until we put a wire. And when we put a wire, there will be electron movement from the blue phase to the green phase, and the ions will go through the electrolyte solutions into the green phase. Okay, so this is a discharge of the battery. Oh, this is names. This is anode, this is cathode, this is the electrolyte solution. And when we discharge the battery, we really put electrons from the reducing phase, the donor, into the oxidizing phase. And this is how it looks. And then when the ion movement, they come from the blue phase, from the anode, into the cathode. This is when battery is discharged. When we want to charge our battery, we plug in into the charger, and then we are forcing the thermodynamic to go back. We put 5 volts instead of, so this, I will show you the voltage later, but we are biasing this reaction to go back. This is against the thermodynamics. So when we are charging, we really take the lithium ion back, and then we can really discharge the battery. So it's a rocking chair in a way that the movement of ion is like, it's like a rocking chair. So from the anode to the cathode and vice versa. What's really interesting for us is that the electrodegradation or the material degradation upon cycling of the battery really takes place through the interface. So there is also a surface film formation on both the cathode and the anode. And as we cycle the battery, the formation of this film is really important for the continuous operation of the battery cell. In fact, the first one to introduce the model is Professor Emmanuel Pellet from Tel Aviv University that showed that this electrolyte is decomposed on the surface of the anode to form a very thin film solid electrolyte interphase. It's a new phase which is very thin on the anode side. Thin is in the range of few tens of nanometers that allows lithium diffusion through it, but then suppress the reduction of the electrolyte solution. So the reactivity here stops, but only lithium ion movement continues to go, and then there is a kinetically stabilized battery. This is how the lithium ion really works. So if we look on a battery cell, we have the anode, we have the cathode, and now we want to choose a better anode, a better cathode to have a next generation battery, and this is how we go in terms of choice. We have, this is one, so on the y-axis, we have capacity in milliamp hour per gram. I will dive into it in a second. And here, it's the voltage. Voltage means we translate the thermodynamic of how much the anode is really interested in reducing the cathode. So don't know how really he wants thermodynamically to give electrons to the cathode. This is what dictates the voltage. The capacity, for example, let's look on graphite. If we start with graphite, which is the currently used anode, this is graphite without lithium in it, and it can take in the middle of battery operation, if I'm charging it now to lithiate the graphite, it will go through a carbide of lithium C12, so one lithium on only 12 on every 12 atoms of carbon, and when it is fully lithiated, it can only go lithium C6. So the maximum amount of lithium that can be hosted in graphite electrode is 1 lithium per 6 atoms of graphite. So the capacity here will be translated to the values above 300. This is what limits the current technology. We have limited ability of the anode side and the cathode side to host lithium in it. So if we want to have higher energy, we need the anode and the cathode to be as far as we go in terms of voltage. And then we will also want them to be as high as we can in terms of lithium that can intercalate or even react with it. So the more lithium, the higher the capacity, and the more distance in thermodynamic value for reduction, the higher the voltage. then the higher is the energy. So as potential candidate, we can think of lithium metal or silicon. This is where we are. This is where graphite is in terms of capability to host lithium in it. And metallic lithium can obviously host more. Silicon can also host more lithium in it than graphite, 10 times more. This is the anode options. The cathode options can go. This is the currently used cathode, lithium cobalt oxide, and we can think of phosphate material which are higher in voltage and also higher in capacity, and also oxides that are higher in voltage and capacity. Oxygen can also be a very good cathode. Sulfur, elemental sulfur can also be a very good cathode. Now, when someone is looking on this chart, he can think, okay, let's just conjugate lithium metal with oxygen or lithium metal with any kind of cathode we want, and then we have the next generation battery. It is true. We can really run a car from the Eilat to Hermon using lithium and oxygen. The issues there will be not related to the questions of capacity and voltage. It will be related to the interfacial stability of this material and also to the reversibility. So what this chart is not telling us is all the issues related to the sluggish kinetics, to the electrolyte instability on the surface of the active materials, and also to the electrode itself that might degrade as we operate it up. So this is the real situation within. Remember, this is current collector, pasted active material on the anode side, pasted active material on the cathode side. We can see that the situation or the electrochemical conditions within a battery cell is really complex. This cartoon is trying to demonstrate the complexity. Many interfacial reactions, many instabilities of the active materials itself or the contact between the active material and the current collectors. And many of these issues really require a solution in order to move forward for a next generation battery. So I will now focus on a choice of one active material as an example. So this chart is telling us that the lithium cobalt oxide, the currently used cathode material, can demonstrate 150 milliamp hour per gram. So the capacity of lithium cobalt oxide is limited to 150 milliamp hour per gram. It's half the capacity of the graphite. Theoretically speaking, we could have more. So if we take all the lithium out, we can have more. But the voltage for taking all the lithium out is too high. So we are oxidizing the electrolyte solution. This is not an option. This material, the one I showed you before, and I will go back to it later in 2 slides. This material is really capable of delivering in lab, measured in lab, twice as much as the lithium cobalt oxide. So if we can take this material and stabilize it, we can use this material and have batteries with twice the amount of energy. This is really how we dive into the material itself. It's actually a composite of 2 different components. One is monoclinic lithium to manganese O3, and the second one is rhombohedral layered structure. And in order to make this structure work, we need first to charge it. Stick with me. Okay, just how this chart is translated. Now, look, we close the battery, as I showed you before. We have graphite anode, which is now without lithium in it, no lithium in the graphite. And there is a cathode of this complex oxide. This cathode is full of lithium. And now we want to take the lithium out from the cathode and put it into the anode to make it intercalate into the graphite. In order to do so, we go and plug our battery and force the thermodynamics to go back. So we are biasing the positive voltage, taking the lithium out from the cathode and sending it to the more negative electron. As we start to do so, the lithium is leaving. So a lithium plus is leaving the active, the cathode material, solid. When lithium is leaving, there is a compensation of charge. The compensation is being conducted through changes in oxidation numbers of the transition metal. So the first thing to take place will be cobalt 3 go to cobalt plus 4. And then nickel can go to nickel plus 4. Now you can think of this chart as very similar chart to phase diagrams. We are changing the phase of the material, but instead of having temperature and pressure, we are having here a content of lithium versus voltage. So we are using a bias of voltage and changing the phase of the material. This is one phase change, and this is another phase change, and this one is a third one. So as we go up in voltage, we take more and more lithium out, and we are changing the active material. When we are changing the active material, not only the desired reaction takes place, but also undesired reactions. For example, nickel can migrate from its position and takes the lithium ion place. If lithium used to be between the layers, it used to be interstitially diffused in between the layers. Now lithium left and nickel plus can take its place. This is undesired because when we will want the lithium to go back in as we discharge the battery, it will be clogged. The nickel will clog it, or it took its position. Another thing that can take place is oxygen release from the surface. These materials, when synthesized, they are rich with oxygen on the surface, and the oxygen is sometimes bound, not strongly bounded. So it's kind of loose. And when we go to high voltage, there is evolution of oxygen. I will show you how we measure it later on. And the oxygen, when it is evolved at high voltages, it is reacting with the electrolyte solution. So there is interfacial evolution of oxygen and then immediate reaction with the electrolyte solution to form thin films, which are also clogging lithium from moving. So the challenge is really stabilizing the material and preventing the interfacial reaction. So what we are doing, we are coating this material with thin films, as I showed you before. So you remember we were capable of really coating the material. This is the TEM of the material with the thin film that I showed at the beginning of my talk. And when we want to diagnose the effect of the efficacy of this film in preventing or suppressing the evolution of gas, for example, we are using online electrochemical mass spec. So we have a unit which is connected directly to a battery. And then we are, you know, that when you look on the battery is swollen after a long time. That means that the alkyl carbonate solution, the solution can turn into a gas upon repeated reaction. As I showed you, when we go higher in voltage, there is oxidation, and then there is evolution of gaseous species from either the solvent or the lithium salt. And these are swelling the battery, and they are now making all the layers that I showed, they are no longer intact. So the connection is not good, and we cannot operate the battery. We are following it in operando using online electrochemical mass spec. We have mass spec connected directly to electrochemical cell, and we are using it in order to follow the evolution of gases. For example, here, carbon dioxide evolution. This one is the treated cathode material, and the blue one is the untreated. It is connected to the mass spec, and we can follow as we discharge and charge our battery. You are already all experts. We are charging the battery to high voltage, and then we charge it, we discharge to low voltage. So lithium is out, lithium is in. Lithium is out, lithium is in, and we are now following the evolution of gas. So here we can see that the carbon dioxide evolution is suppressed when we are treating the active material. And also the oxygen evolution is suppressed when we are treating the active material, but not completely killed or not completely disappeared. We are working on that, but it is suppressed by the surface spin. We can also follow it by the electrochemistry. Again, you are an expert. So charging, this is going to positive, and then discharging, we put the lithium back. And we can see that we gained a little bit in capacity, meaning with the treated one, we can put more lithium back in. And as time passes, more cycles of the battery, charge and discharge, charge and discharge. Time passes, we can see that the capacity of the treated one is higher than the untreated one. Meaning that by suppressing the evolution of gases, we improve the stability and we improve the capacity. I will also demonstrate it in a second in terms of morphology of the particle. But one thing that I want you to look is here. 4C, language, 4C means that I'm discharging the battery in a rate that will enable me to fully discharge the battery 4 times an hour. So this is a very fast discharge. Means I'm challenging the kinetics of the reaction. For the user, it means he is discharging the battery very fast, so it's high load. But for the chemistry, it means that I'm challenging the chemistry, the kinetics of the chemical reaction. And only when I go to high rates, I see that the coating of alumina is not fast enough, meaning that the permeability or the mobility of the lithium through this thin film is not optimized. I will show you later. I want you to keep this number in mind, the 4C. how we also tackle this problem. This is how the particle look like after cycling. You can see the cracks of the untreated one already after 30 cycles and more severely after 50 cycles. So we just open the battery cell, go to the microscope and look on the particles. And these particles are the particles I told you that are 5 microns, about 5 microns in diameter. You can see the cracks here, and these are the treated. So this is the treated particle after 100 cycles. So again, taking the full electrode, which is pretty large surface, and going particle by particle is an issue from statistical point of view, but we couldn't find the cracks, or at least they were not obvious as we looked. And it is also in very good agreement with the fact that the evolution of gas that takes place from the surface of the active material is suppressed. How much time do I have? Huh?
15 minutes.
1.5?
Good.
Okay, so we then demonstrated the same thing with diethyl zinc as the precursor. And the interesting thing about the diethyl zinc is that we were, so my postdoc, Dr. Arka, he managed to, I will show you here. So what he did, he changed the temperature and he followed what is going on to the thin film if we are running the reaction at 2 different temperatures, 100 and 200 degrees Celsius. And we could find that in the 100 process, it was easy to detect the presence of zinc as we are depositing the zinc on the surface of the active material. But when he moved to the 200 degrees, it was very hard to detect the zinc with X-ray photoelectron spectroscopy. But when we moved to elemental analysis, the zinc was there to the same extent. So we're using ICP, inductive coupled plasma. We can see the zinc is there to the same extent. So for us, it suggested that something is going on the surface and then zinc is penetrating into the depth of the cathode. So we were also able to demonstrate it using top sinks and STM. So this is the 100 degrees centigrade. You can see that the zinc is on the surface. But when we are moving to 200 degrees process, the zinc is penetrating to the depth. It was very good because previous works have shown that zinc doping is improving the stability. This is different cathode material. It's a more interesting for the industry. This is under the consortium of BEARD, which is the US-Israel BEARD consortium that I lead. This work is with an American company called Xaft, now bought by Total. And this is a very interesting cathode for the industry. And we are capable of treating the surface and improving also the electrochemistry. What you can see here is that this one is the 200 degrees, so it's coating, but it's also a near surface doping of the active material. We are capable of showing stability for the treated of the 200. So this is the capacity, how much lithium can go in. We have more capacity and also better stability. And another thing that is obvious if you look on the chart here, this is maintained. And as I told you before, the voltage here tells you a lot about phase. So it's a phase diagram. So the maintenance of voltage also means that you are maintaining the phase of the active material. And the material itself is degrade pretty fast when it is unprotected, but it is stabilized when it is protected with the optimal process in terms of composition and surface morphology. Again, when we look on the material when it is bare before cycling, this is NCM after cycling, the nickel cobalt manganese oxide. You can see many cracks, and these are the cross section of the protected one. This is how it looks. So significantly less cracks in the active material, which is protected after 100 cycles of operation in a battery cell. The next thing I'm going to show you, or the last one, is how we protect our active material using the more complex process. Instead of 3 elements for coating and then alternating sequence of 6 steps, we are alternating sequence of only 2 steps. This is in a collaboration with Professor Apeloy from the Technion and Dr. Michal Exlitz from the Weizmann Institute. This is the coating I showed you in the introduction. It's a lithiated silica on the surface of the active material. I will come back to that if we have time. This is very interesting, but the importance here is that we have 2 steps. Instead of multiple steps that people tried to create this thin film before, they either failed or they could not control the conformality of the thin films, or it was a very complex process of too many steps for becoming really practical. Now, I told you before to keep in mind the 4C. This is the high rate discharge, meaning we are discharging the battery 4 times in an hour. This is the alumina coating or the surface reduction of alumina, and this is the bare one. And we have 41% improvement for the lithiated silica. There are many works, mostly theoretical, that the importance of lithiated version of the coating is very high. When you go to thin films and you go to high rates, you need the lithium mobility to be very fast for the interface. So the work of mostly Catherine Pearson, she's really calculating the importance of the lithium inside. And what we demonstrated here is that the lithiated version of the coating really enabled us to achieve high mobility of the lithium. It was also demonstrated experimentally by again, Dr. Michal Eskes from the Weizmann. What she did here, using enriched by isotopic enrichment of the cathode material, and then a dipping experiment, following the exchange of the lithium isotope with the abundant lithium in electrolyte solution using solid state NMR, and she could follow the kinetics of exchange, and the fastest the kinetics you can see here. The kinetic is faster when we are coating our material with the lithiated silica film, meaning strongly supporting our finding in terms of electrochemistry that really the coating facilitates higher mobility of lithium through the interface, therefore enable higher kinetics. Again, the evolution of gases is significantly suppressed, and when we are looking for cracks after 100 cycles, this is how the protecting electrode looks like, and this is how the unprotected one. So significant cracks, which is also associated with gas evolution, is suppressed by the fact that we are putting a thin film on the active material. What is interesting that when we look on the chemistry of the thin film, and we are really almost half blind, because what we can do is we take the thin film to high resolution TEM, and then we can see the morphology. So we can see the existence of the film on the surface, but telling things about the chemistry is complicated. We then need to move to yields or to other techniques that really tells us the oxidation number. But when we are doing so on already cathode material, which is enriched with lithium, it is a challenge. We can't really, it's very hard to differentiate between the various origins of lithium. What Michal was capable of doing for us, and it is really important here to look on these two. This is using solid state NMR with a special dynamic nuclear polarization techniques that she introduced a radical, and then she can dynamically polarize the element of choice, or what we are looking. She was looking here on the silicon. And what you can see here is that the inorganic silicon, meaning the silicon oxygen, is more, it exists, but it's smaller in intensity compared to the remaining organosilicon-based thin films. Now, the interpretation of this data means that in close to the inorganic material, we have more inorganic silica-based thin film. But as we go out from from really the contact between the electrode and the thin film, which is more inorganic, when we move out, and it's out in 3 nanometers. This is how she is capable of looking. This is how sensitive her methodology is. When we move out, we are capable of seeing more and more enrichment of organic moieties that are remaining from the process. This is very good because it also facilitates better wetting with the electrolyte solution, and the importance of these oxygens in lithium mobility is also well reported. So for us, it was a very interesting capability to really see what we are doing, thanks to Dr. Leskes. And this is really a full cell. This is a real battery. closed here at Bar-Ilan. We have a pilot line for battery closure, and this is a capacity of more than 200 after 200 cycles. This is very good. This is much better than the currently exists battery technology. So I hope that I showed you today that functional materials in batteries mostly degrades through the interface, and that scientifically informed choice of thin functional protection area can fix the interface and help in mitigating the battery degradation and failure. Online electrochemical mass spec is also a useful tool for us to really see if we are suppressing the evolution of gas as we are cycling the battery, and we're capable of, we show that manipulation of the ALD and molecular layer deposition processes enable us to achieve desirable functionality of the thin film of the active material. And this is more cartoon-like summary of my talk. Yes. I want to thank again my group here in Corona days at Bar-Ilan University, and here in more happy days in yes, Amon Hatziv. And thank you for listening. I'll be happy to take questions.
Yeah, so you talked about lithium batteries. I mean, is there a reason why everybody is focusing now on lithium batteries? Another thing, I mean, in improving the batteries, what about the safety issues? I mean, why batteries explode and sometimes, and what do you do to avoid such events?
Okay, many interesting questions. Okay. So first, the question about focusing on lithium ion. Well, the good thing about lithium ion is that it really works, and other batteries are not mature enough like lithium ion. We are also working in my lab, and we are working also on sodium ion batteries. So if the cation there will not be lithium, it will be sodium. The only reason to go there is because sodium is much more abundant. So the price of the battery goes up. We need to have lower price, and this is the only reason to do so. Because lithium is small, this is why it works perfectly fine. You can find active material which are solid, and you can demonstrate high lithium mobility in room temperature. It's very challenging for larger cations like sodium, or for the valent cations with the same dimensions like magnesium 2+. You can think of same dimensions, but when magnesium need to intercalate into a transition metal oxide, then there is a 2+ on every cation. So it's very challenging for it to diffuse. So the interfacial diffusion is sluggish in magnesium case. So the reason to work with lithium is because it works. There is why to shift from lithium is because we do not have enough. The price of the systems will go up. So now there is a movement to sodium ion. I have worked on sodium ion and magnesium ion. Soon I'll start a project with zinc. This is how this is why. Now you had more important questions about why lithium. What was the second one?
About the safety.
Safety. Yeah. So I did not touch today. So sodium, indeed, another reason is that sodium potentially might enable use of electrolytes which are more safe than lithium. So the solvent used for lithium are flammable, and also the lithium itself as a battery, because I showed you that the reaction is really spontaneous. If there will be a shortage inside the cell, there is a thermal runaway. And this is what caused the explosion. The anode really wants to reduce the cathode in a very spontaneous and also exothermic reaction. And it is all going on in the presence of electrolyte, which is actually organic electrolyte solution, highly flammable. So what you see here is really a failure of the battery. There was one company. I'll go to the form factors. So there was one company, I will not mention for obvious reasons the name of the company, the cell phone company that really called back. Yes. I don't know why you're laughing. So when you look here, they took scientists from the top-notch groups, and they showed that the welding here was really the cause for explosion. Because when you have a welding which is not completely well done, when you apply a voltage, so you can think of the fields over there, it's enhanced, and then the deposition takes place on a single spot. And if you're creating a hotspot for deposition or for negative for lithium intercalation into graphite, if you slightly go to a more negative voltage, there will be a metallic lithium deposition. And when lithium is deposited metallically on the surface, you will have a growth of a needle of lithium that can penetrate all the way to the cathode, and then there will be a thermal runaway. And then you have explosion. So moving to a more safe electrolyte solution is mandatory, or it's really important, especially if we move to high energy material. So the high energy means we gain more energy, but most of the time we lose in safety.
Yeah. So can you guide us through the thinking process? How do you decide what to grow on?
Yes, good. Very good question. Thank you. So when I'm thinking about what I'm going to have on the surface of the cathode material, I need to have a few things in mind. One, it needs to be lithium-ion conductive, or it's better to have a reasonable ionic conductivity. You know what? Number one is that I can have available compounds to really create this safety. So number two, I can't really imagine that I will put lithium niobate is an option. I can put it, but the price there is killing. So there are many parameters. But here I need to think that my thin film needs to be stable. Otherwise, it will decompose. I will form an interfacial reaction of the film itself, which is highly undesirable. Otherwise, it will not exist after the first cycle of the battery. It needs to be lithium-ion conductive. It needs to be very good contact with the electrode itself, because otherwise the interfacial resistance will be increased and not decreased. And it needs to be stable in the environment of the electrolyte solution. So these are the main
no, but is it like trial and error, or
no, it's not trial and error. If I will put phosphate in this type of material, I showed you before that I'm putting lithium. It's a phosphate-based system. If I will put it here, it will not be a perfect idea, because the thermodynamic stability of this coating itself is not crossing even the 4.3. So I can't put it in this material. So it's after I'm succeeding, then it might be a try and error trying to put zirconium into the silicate film. But we chose the silicate for a reason. It should be stable there.
So one question, you showed here an improvement of about, let's say, 40%. What would be considered a success or good enough? I mean, anything is better, but what is game changing?
Yes, thank you. So this is a very, very important question, because if I will show a 40% improvement, I showed it in 4C, so in specific rate. If I will show a 40% improvement, but the cost of the active material will then be 20% more, it's not a solution. Okay, not for EVs, maybe for military application, it is a solution. So Rafael are here coating in my lab, they are coating, and the price is less important for their application. So first, it depends on the niche of application. If we want to go to EV market or to large energy storage, then the improvement needs to have few facets. One is you improve the capacity, so you improve the energy density of the cell. Second thing is improving the longevity. How long is the battery operational? So the longer it is operational, the more likely it can become a solution for large energy storage, for the grid or for load leveling. And the third thing is safety.
Are there any questions from home that we missed? So
yeah. How about the recycling process? Once a battery runs out of its lifetime, what happens? It becomes a complete waste, or it can be recycled? Thank you.
Okay, so the question was about recycling of the active material. So right now today, the technology is really in a progressive stage, way beyond the capability of recycling, unfortunately. The recycling is very important for all the cobalt-based materials and also the nickel-based materials, because the price of the nickel and the cobalt went up. The abundance of cobalt is an issue. This is why the community is shifting away from cobalt-containing cathode. Now, recycling is going on in parallel. I have a project of recycling with Israel Chemical, with ICL, with Chil. The early used to be here. So I have a recycling project with them. Today, the recycling is in a premature. They shred the battery, they take a black mass, and then by chemical etching, they are reproducing the nickel hydroxide, the cobalt hydroxide, and then you can reproduce a cathode out of it. This is where the recycling is right now at. The copper is also very important. The current collectors of copper is also very important, as we will have more and more solutions of lithium ion on the market. The copper will become an issue. And then recycling of nickel and cobalt are the leading things in terms of recycling. The other thing that people are looking at is second life. Before you, so one, if the battery is dead for electric vehicles, it doesn't matter, you can't use it as a second life for a large energy storage solution. So you might gain some more years of operation from a single cell before you go to recycling.
But none of their components are kind of polluting or poisonous to water systems or what those kinds of issues are not there in these batteries.
Yes, cobalt is. Lithium is also a problem, but it is all encapsulated. So when you move to recycling, you are just decapsulate the battery and you take every compartment separately. You either shred it or you dissolve it and precipitate again the active materials.
Okay, so thank you very much, Malachi.
Thank you.